Hello everyone. So right now in this video I will be presenting or explaining, elaborating, discussing with you the idea for modulus equations, and then in particular about the type of modulus equations. As you can see over here, there are three types of them, and then how you solve modulus equations by, in particular in this video, it's how to solve the modulus equations by using the concepts. In the next video, you will see later how I will explain to you how we should be solving modulus equations by squaring both sides, which probably for many of us, it's the method that are so preferable. But in the case of this video, I will ignore this. That will be the focus of the next video. Okay, so first of all, before we go through discussing the idea on how to solve modulus equations, it's important for us to know what modulus equations are. So as the name, of course, it is an equation involving modulus functions, right? So as the name, modulus equations, yes, equation involving modulus function. So basically in the additional maths IGCSE or probably O level as well, there are three types that we are discussing, as you can see here. The first type, which is the modulus function and a number. The second type, which is this one, the modulus function and a linear function. And then the last type is the modulus function and also a modulus function and linear function in particular. In particular, in the additional maths soup embedded textbook that we use at school, these two types, these are catered in chapter 1 functions. Since we are currently discussing chapter 5, this is the part that we are discussing in chapter 5. But in particular, or in general, this is what we basically learn in modulus equations. Actually, there are still some more. Of course, there is still the quadratic modulus as well. There are other types as well. But then the focus of the linear equations, maybe we can particularly or specify this as modulus linear equations. These are the three types that we are discussing. So before we go through and then discuss how to solve the modulus equations, let's revisit what's the definition, which I touched on this in chapter 1 functions back then, or in chapter 2 as well. So what is a modulus function? It's symbolized this way. For example, a modulus or an absolute value symbolized by the two lines, the two vertical lines. This modulus function x can be presented as x or negative x, right? But then for each of this, there is a restriction for this, right? For example, why is it like this? For example, I can present it like, for example, like this. Let's say a modulus of 4. Modulus of 4 is 4, but the modulus of negative 4 is also 4. So then the modulus function, it's making sure that the value or the output value must not be negative. 0 is possible. So for example, modulus of 0 is also 0. But then you see why we are using these two definitions or this meaning, because for example, in this case, the example before, right? The modulus of negative 4 becomes a 4. Basically, what did we do? We actually make it negative of the negative 4, right? So that's falling under this area. So that's why whenever we have below negative, we add the extra negative over here, so then it becomes a positive or it becomes a non-negative. But then does it always have to be 0? In this case, no. In this other case, in this case of modulus x, yes. But then for the other types of function, of course, it's different. For example, this guy, modulus of x plus 2, it can be x plus 2, right? Or it can be a negative of x plus 2. When you see the domain, it's x at least negative 2 for x plus 2, or x less than negative 2 for making the function to be negative of x plus 2. And then you should notice actually by using the graph, for example, when you try to sketch the modulus of x by using GeoGebra, for example, or any other software, or you just sketch it on your own, the shape will look something like this. Y equals x itself will look something like this. right? But then when you want to have a modulus of x, this one should go up instead. So this should be the function that we have, for y equals x modulus. Right? So you see this part, actually it's not there anymore. And then you see the key point is this, in this case is 0. But then whenever you have the modulus of x plus 2, for example, x plus 2 in general will look something like this. This is y equals x plus 2 only. But if you want to have an x plus 2 modulus, so starting this part, it must go up instead. So it's like a reflection of the one over here, it's just reflected, right? So I'll put it here, it's like a reflection. Reflect. Okay? So that's why here, whenever you take a look or notice this is the x-intercept, right? And then in this case, the x-intercept is x equals -2. And this -2 is what we are using here, right? As you can see. So that's why I can put a note over here. It's basically coming from the x-intercepts. So the number 0, the number -2, the number 1/3, they are coming from the x-intercepts. So then we can use them as the domain, or in the domain. So for example, you have another one, the modulus is 3x minus 1. Again, it can have two values when x at least 1/3, again, from the x-intercepts. 3x minus 1 equals 0, x equals 1/3. When x at least 1/3, this should be the value that we have. But whenever x less than 1/3, instead what we have is negative of 3x minus 1, as you can see over here, right? This two. So these are the definitions, not these are, but this is the definition of modulus function, which we will be using it over and over again and whenever we solve modulus equations by concept, as well as when we see how we solve modulus inequalities later, again also by concept. So let's try. So in this case, let us discuss how do we solve these three examples of modulus equations. The first one, given modulus 2x minus 1 equals 3. So how do we solve this? By the concept, as earlier as discussed, the modulus of 2x minus 1 must have two values, right? 2x minus 1 and negative of 2x minus 1 when x at least half here and x less than half. So this will be the key properties that we need to consider. So that's why you see here when x at least half, consistent with this, right? And when x less than half, consistent with this as well, right? So then you see when x at least half, that's why I still use 2x minus 1, and then here it's the negative of it. And then you solve it as per normal linear equations, and then you get x equals 2 and x equals -1. However, these are the notes that is really important in any algebraic work. Possible algebraic work doesn't necessarily lead us to the final correct answers. Okay, why? So this is the case, for example. So whenever you have these two possible solutions, x equals 2 and x equals -1, you have to check back again with the domain or the restriction that we have. Is it really true x equals 2 is more than half? Turns out, yes. So it's a good thing here, right? And is it really true that x equals -1 less than half? The answer is yes. So in this case, yes, both of them are the solutions. So remember the practice. We have to check by using that, or you can also check it by plugging here back, substituting here back to the equations, and then you make sure is it correct or not. That's also another possibility. But then since I'm trying to use the concept, so I really stick to how we do it by using the concept. So let's see that practice again. We'll use it again. So now dealing with type 2. Type 2, this is what we have, right? 2x minus 1 modulus equals 3x plus 1. Same thing. Since this is modulus, so we have to separate it into this and this again, right? So when x at least half here, and when x less than half, so we do the same thing. So that's why you see 2x minus 1 equals 3x plus 1. we solve it, and we get 2x equals -2, and then here you have the negative of 2x minus 1 equals 3x plus 1. Again, I refer to the definition that I already write here. Then you solve the equation as per normal, so then you get two possible solutions again, x equals -2 and x equals 0. And then again, you have to check. You have to check against the domain that you have. Is it really true that x equals -2 is more than half or more than equal to half? Turns out it's no. You see here, right? Turns out it's less than half. So that's why x minus 2 is not a solution. So see here, it's not a solution. The same is true when x equals 0. Is it really true x equals 0 less than half? Since it's a yes, so it's a solution. So then by having these two checking, so we can be sure that x equals 0 is the only solution that we have for this case. You can also check it again, like what I said, you can check it one by one. You can just plug in, for example, here, or you can use graph, like in this case. Let me explain to you by using the graph first. So if you're using the graph, basically you sketch both of them. Whenever you have this type 2, remember chapter 2, simultaneous equations, this means you basically have one function and one function, right? Y equals 1 plus 2x minus 1 and y equals 3x plus 1. Those are the two functions that you need to sketch. So here, you sketch the two of them. Let me just present, because this is already the final answer, let me just present to you once again how we can do it, right? Whenever you want to sketch, of course, you present the xy first. And then, let's say I want to sketch the 3x plus 1 first. I have to know how I sketch 3x plus 1. So I know the 3x plus 1 will look something like this. If this is 1, so it will go something like this, really high, right? I know this is y equals 3x plus 1. Now, how about for the y equals modulus 2x minus 1? So I'll do it by drawing first the 2x minus 1, which is, I will need here, -1. If this is 1, so I will probably have something like this. It's 3x plus 1, so I should be having, wait, this is half. I think this one I should draw it a bit more steeper. Sorry for this. Should draw it probably somewhere here like this. Okay, that's better. So this one I will probably have something like this, right? But then no modulus, right? Because modulus there is no below that, so I should be having this instead, like this. So then you see I have one intersection over here, right? So I'll change the color, sorry. I'll have one intersection here, and then if you sketch it properly, you can tell that these two graphs, these two lines will never meet again. Never meet again. Again, as x goes to infinity, like x goes to so large, and then it will never meet again. So here you can check, yeah, there's only one solution. There's another way to check. This is check using graph, right? Another way to check is that plug in. Just check by substitution. That's also possible. Then this is probably one of the most preferable method. So whenever you try x equals -2, you plug in back to -2, -1. So you get, is it the same as 3 times 2 plus 1? If it's not the same, then it's not okay, of course, not part of the solution. Or you can just see it here. This will give you negative values, right? This is negative value. So then, of course, this is not the same. So that's why x minus 2 is not the solution. And when x equals 0, you plug in also 2 times 0 minus 1. And then here, 3 times 0 plus 1. And you see they're the same, so it's good. But this one is no good. That's how you check. Okay, so let's now move on to the last part. 2x minus 1, the type 3. Type 3. Modulus 2x minus 1 equals modulus 3x plus 1. So same thing, but then since we have two modulus functions, so we have to have this two. So we already have the first one. Let's make it for the second one as well. So here, already present for you. Now, the tricky part for this is that we have to separate the intervals into 3. Why? Because we will have, whenever we try to sketch, if it's only this, then it's fine, because we only have like either this or this, right? But then if we also have this, then it makes it unclear which one that we need to check. Do we need to check like for really each of them, like 1, 2, 3, 4? That's too many. So the way we know how many that we need to check is that we draw this number line. This is the x, the horizontal number line, and then you plug in both numbers, the key numbers, negative 1/3 and 1/2, right? And then you see, based on this, there are actually 3 intervals. Let me just erase the 0 here. There are 3 parts. One, the most left, the second is the middle, the third is the most right. So let's separate for this 3. So when x less than negative 1/3, you have to check again based on the definition. So if it's x less than negative 1/3, so you will be using this one, and this is also what you need to use because it's less than negative 1/3, right? So you can check it again, and then you do the solution for each. You try to solve the equation. You do the same for the middle one. You do the same for the right one. So you can check first how I did it here. When x less than negative 1/3, so I have this negative and negative. But then when x at least half, I have this both positive. So whenever you see this 2, actually the type 1 and type 3 give us exactly the same answer. But the unique one is this. When the value of x is between negative 1/3 and half, I have to use this negative of 2x minus 1 and 3x plus 1. So you can check that again from here, from the upper part, right? Then you will see that will be the correct way. Then we get x equals 0. Then what to do after that? Again, checking either by graph or checking by using the domain, the restriction again. Like for this, you know, x, let's say I'll do the checking here. X equals negative 2, it's less than negative 1/3. True. So that's why that's part of the solution. While here, this is not part of the solution because you see x equals negative 2 is actually less than half. So this is not true over here, right? But this is true. Now in the sense of this, x equals 0 is in between, right? So this is true also. So x equals 0 is between negative 1/3 and half. So it's okay. So that's why you have two solutions, the x equals 0 and x equals negative 2 as the final solution. That's checking by domain, or you can check by the graph, or you can check by the substitution. They will give you all the same answer, right? So which that leads us to the conclusion that you will see also in the second video. For modulus equations, there are basically 3 methods to solve, but then for the sake of simplicity and convenience, I will not be using the graphs. That's the most inaccurate method for you to use because we don't use GeoGebra or any graphing software whenever we're dealing in the exams, right? But then at least you have to know how. In this video, I covered the concept way, but in the next video, you will see how I deal with the squaring both sides method, which is probably more expedient, but then you still have to understand why. The second conclusion is that the way we solve modulus equations will be the basis for us to solve modulus inequalities later. Will not be exactly the same, but you will need the concept. And then the third one, you have to kind of advise to check the solutions always, especially for the type 2. Why? Because this type 2 is really important because this part is possible to be negative. So it's something that you have to be really careful of. So before I end this video, let me just show you one example from the exercise 5.1. Let me take on the discussion for this one. This one you can see in the second video later. So let me take on, for example, question number C. Right, question number C over here. So let's say we have modulus 2x minus 3 and modulus 4x minus 4 minus x, and then we want to equate them. So as I did before, so I will have to break it down into this. And the interesting part is this guy. You see, it's a bit different from this one, like the pattern. Whenever x is at least the key number to intercept, usually we don't change this way, right? We just keep it the same. But in the sense of this, the x at least 4, you see it's like the other way around. So it turns out you cannot always just use the pattern like that, but you have to kind of check when x equals at least 4. Let's say x equals 5. Let's say we check. If we consider it should be 4 minus x, let's change it into 5, and it will give us -1 instead, and that is incorrect, right? We don't want to be having a negative result. We want it to be positive or non-negative. So to get plus, it will be negative also. So it will be a +1. That's why we need to have this negative over there, right? So, or you can make sense of that by using the graph. 4 minus x, or y equals 4 minus x, will be having graph like this, right? But if it's a modulus, then we have to reflect this part. In that sense, if this is a 4, when x at least 4, you have to do some reflection. That's why there is the negative side over here as well. That's how you kind of make sense of it as well. So here we are, same thing like before, we have to make the number line, and then we have the interval 1, 2, 3. So then that's why here you see there are 3 intervals for you to check. And then you use again the properties that we already have over here. So you can check and then see first for a while. You can pause the video to see for x less than 3 halves, for in between, for x more than equal 4, which equation that we are using. There's 1, 2, 3. So please do have a check. Then after that, you solve each equation, right? The possible solutions are x equals -1, x equals 7/3 or 2 and 1/3, and x equals -1. And then you see it again, I check each of them against the domain, right? So this one less than 3 halves, so it's good. And then this one 7/3 is also in between, so it's good. That's why there's a checklist here. The last one, x equals -1, is not more than equal 4, so it's not a solution. So in conclusion, the solution must be this. And you can check it by using any other software if you wish. So here we are. I'm stopping the video here for the modulus equations by concepts. You will see in the next video I will discuss the modulus equations also, but by using squaring both sides. I already presented here. We already have the discussion. You will see later. I'll be using the same exact 3 types. Then I'll show you how we deal with this differently. Okay, thank you. I'll see you in the next video.